So thank you for the introduction. I'm going to basically continue where Siddhartha left off. So he gave a very, very nice introduction to the match statement. I'm going to talk a bit more about advanced features that you can use and also show a lot of examples that go a lot more in depth on how you can actually parse things. So who am I? I'm Marc Lemburg. I've been around for quite a while. Actually, I should probably no longer say that I've been doing Python since 1994 because that's like 30 years ago, so I'm old. So anyway, I have a consulting company. I'm doing senior architect work. I've been involved in the Python community a lot. Python Software Foundation fellow, core developer, EuroPython Society fellow, lots of stuff. So let's jump right in. We already heard about the match statement. This is how it looks, just to basically give you a reminder of what happened about a half an hour ago. This is the match statement as you typically write it. There are actually quite a few things in this match statement, and it's actually quite busy. If you look at the PEPs that define the match statement, there are a huge number of things that you have to know in order to understand the match statement. So everything starts out with the match object, which is up here. I don't know if this works. Let me see. No, it doesn't. So anyway, oops, sorry. So up there, the object obj, that's the match object. That's basically what you want to match. And then you have all these patterns in here next to the case. So those are called type patterns. Well, the first ones are called type patterns. The other ones are called instance pattern. And then you can have a sequence pattern and a mapping pattern. And then you have a wildcard pattern down here. I usually basically give it a name, but you can also just use a single underscore for that. So that's basically matching everything that you can put into object. I'm just going to very briefly go over these things. So a type pattern basically matches a type. So whenever you have a list, then you go into the first case statement there. If you have an instance, then you can actually match that particular instance, and you also can look into that instance and match attributes of that instance. For sequences, you can use a list, like here. Again, you have to be careful. This is not matching a Python list. It's actually matching any Python sequence, right? So if you put a tuple here as object, then it'll match as well. And same for the mapping pattern that you have down here. It looks like a Python dictionary, but actually it's not a Python dictionary. It's basically a mapping. So any kind of mapping gets accepted for this and gets matched by this. What you can also do is you can capture values that are being matched, and you can put those into variables, as I did in the first case there, as list object. So basically whatever matches goes into the list object variable, and then you can use that in your case statement. You can also do that with things like over here. Yeah, so you can have wildcards in there. You can put data that you don't know anything in particular about. You can put that data into extra variables and then use those variables in your case statement, which is extremely powerful, and it's also a great way to do error handling. Yeah, let's say you have extra elements in your dictionary, then you can find those extra elements by looking into those variables. And then, of course, finally, you have the guards. So basically, you can put extra conditions there. So if this matches, you're not entering the case just yet. But instead, what happens is you put all the variables in here into ABC, and then you can have a condition here, which is then applied to that particular case, and you only go into the case statement if that condition matches. So that's also a very, very powerful thing to have and to use. Now, why am I giving these talks? I have another talk on the match statement as well, a simple one, which is kind of similar to what Siddhartha did. I basically decided to do this because I found that the match statement is not being used a lot. And the reason behind that is I tried in 2001 with PEP 275 to get a switch statement, which is kind of similar, into Python, and it was rejected at the time. So I was lucky, 20 years later, we finally had something similar in Python. And of course, I wanted to succeed because I think it's actually very, very useful. And the match statement is a lot more powerful than what I had in mind back then, because basically I just wanted to get the C kind of switch statement into Python. Match can do a lot more, and I'm going to show a few of those cases. Now, there is a project here for PyPI, which is called, it's a bit small here, it's py-code.org. You can get a lot of data about packages on PyPI. And the author of that website also did an analysis of language features used by those packages. So you can actually go in and find out which of these language features are being used by the Python community. And it turns out that in July last year, there were only about 0.5% of all packages on PyPI using the match statement. And given that it's been around for 3 years, at the time of those statistics, it was about almost 2 years. So it's not really used a lot. And every time I do a poll about these things, you don't see a lot of hands go up. So I think we need to have more of these talks. One of the reasons for this, I guess, is documentation. Because if you want someone to use whatever you put into the language, of course you need good documentation for that. Unfortunately, we only have these PEPs. And the PEPs are really very, very technical. The best way to start is PEP 636 if you want to learn about the syntax. The other ones are more about how everything works internally. And if you want to get into the true details, then that is something that you should read. But otherwise, they're not very helpful. And the Python documentation on these things is not very helpful either, because it doesn't give more context than those PEPs. So it would be nice to get a bit more information, a bit more documentation about these things, and maybe a few tutorials as well. If you go on the net and you try to figure out what the match statement is all about, you get lots and lots of examples, but only very basic ones. So some of the things that Siddhartha talked about, you can see on this slide as well, but these are actually features that get used in advanced parsing. So, for example, it is possible to use an OR pattern. So you can use OR matching, and you can have multiple values that match, for example, in the first case there. Another one is that you can do wildcard matching. So you can put values in here that you don't really want to know about. You just want to know, for example, in the second case there, that you want to have a 1 and a 4 in the last entry. You can do instance parsing, which is extremely helpful. Element is from elementary in this case. I'm going to show an example using that as well. So you can actually match on attributes and even go nested, right? I tried to show this in here a bit, because you can use all these different patterns that you have, and you can nest them arbitrarily. So you can be as complex as you want, if you want. You can also put local variables in there. What Siddhartha already mentioned is that anything that looks like a variable, like for example type name in here, is going to be a capturing variable. So whatever the match statement logic matches goes into this variable and gets assigned to the variable. If you want to use a variable that's already defined before your match statement, then you have to put a dot in here. And the dot basically then says to the match statement, okay, this is going to be something that I have to look up in the local namespace. And then you use the value that gets looked up like that. So it's very easy to just put these things into enums, for example, or just have them in classes and then use a dot to access those. There are a few more tricks that you can use. You can have a look at Raymond Hettinger's talk from 2022. He did a lot of extra neat things to get even more support into the match statement. I'm not going to cover those because this is already complex enough. So what do you do if you want to use it? Well, of course, you need Python 3.10 for this. If you're stuck with Python 3.9, then the only way is to basically to avoid the syntax errors that you would get if you put the code into your modules is that you basically have two implementations of everything. One using match statements and the other one using the classic like if-elif kind of construct. And then you do a try import, and then you can have both ways. And then once you move on to 3.10 or probably even better 3.11, which is much faster, then you can just drop the if statement kind of version of everything. So I'm going to go through 3 different topics here, explaining some of the details. First JSON, then XML, and then AST parsing. So let's start with a simple one, JSON and tabular data. So basically this could be a spreadsheet, like a standard table that you put into JSON, and then you want to parse this. There are a number of things that you have to consider here. One is that in JSON, for example, you have numbers which are either integers or floats. And of course, if you want to match these things in Python, you have to match both integers and floats if you want to capture all those numbers. And of course, you have other things like strings, which are easy to match. If you want to do things like the properties up there, where things are nested, then you have to use different logic. You have to nest your match statements. And I'm going to get into that a bit later. So if you want to match a JSON record like that one with the schema that I put on the right, it's actually quite easy. First, what you do is you match the instance. You check whether it's a dictionary. If it is a dictionary, then you open a second match. And this is kind of like a theme that I want to advertise. Don't make your match statements too complex. Keep them simple and use multiple ones. And if the code that you have here becomes too long, then use different methods to match certain parts of your structure, or use different functions for these things. So what happens here is you match on the name. You say, OK, it has to be a string, and you want to capture the value in the variable name. The second is the price. Price can be an integer with price or a float with price. And what you see here is something new. This would be an explicit capture, and this is an implicit one. So what you do in the second case with the price being inside the brackets of int and float, you basically tell match that it should be an integer, and you want to capture the variable for that integer in price, or the same for float. This can be a very nice way to do things. I would not necessarily recommend always using these things because there are certain implications. It's also not supported by all the built-ins, but quite a number of built-ins. You have to look in the PEPs for the exact list. But it is a way to write things quite nicely and quite short. Again, you have the extra here, so you capture any extra variables that are defined that shouldn't be defined according to the schema, and then you can do error processing here. And once you've matched everything, you can go here and process your data as usual. So what you see here are typical patterns. You match things. You put the matched data into variables, so you can do both the parsing and the actual processing in a single step, which is nice. And you can also do easy error processing, right? If you find things that shouldn't be there, or you find that certain types don't match, you can do error processing directly in here. If you want to match multiple of these records, then of course you should open up a new function, or you basically put the code into a different area of your application, and then say, OK, I have many instances, and those many instances should be a list. And then you go through that list, and you parse each of those entries using the function for parsing a single entry. Now, a second example, GeoJSON. How many of you know what GeoJSON is? A few. So it's basically a way to define geodata. In this case, it's a small island here in the Philippines, and it gives you the coordinates and the name of those islands. And you want to match that. There's a standard for this. You can look that up on geojson.org. And if you want to match a structure like that, then I've put the example data there on the right. what you first have to do is you match the instance. You have to check whether there's a type definition. And if there's not, then basically you would say, OK, I can't match this. Then once you know that there's a type, you have to check whether it's one of the valid types. And you cannot do that directly in the match statement. You have to then use an if statement for that, and you define the valid types. And again, you can do the error handling directly in here. And then for the other members that you have in here, you match all the different members that you are looking for, and then you store everything in your data, or you start processing the data. So this is very easy. XML is kind of similar. Now, for XML, you wouldn't directly go in and parse the XML using match statements, of course, but what you do is you take a tool like Elementary, for example, to parse everything, to convert everything into Python structures, and in this case, objects, and then you try to parse the data out of there. So what you see here, this is actually an example taken directly from the Elementary documentation. It has certain country data, and you want to match that country data and extract it from the data set that you get. And how this works is very similar, except that in this case you're using instance patterns for this. So you see here the Elementary element, and then you parse a tag called country. You get the attributes out of those elements, and you take the data and then continue processing everything according to the schema that you have for these things, and you extract everything. And then, because this will always give you string data, you then can convert everything into data types that you can actually process. For example, the rank you can convert to an integer. The year as well. For the GDPC, you're going to use the float. And then you can store extra data, for example, the neighbors. Neighbors can be an arbitrary list of neighboring countries. And you put those into a new data structure that you create over here with a dictionary, and you put all the data that you find in there. And then finally, you store everything here in a country's dictionary, and you can then process the data. So this is a very, very clean way, a very easy way to write a parser for this data. If you do that using if-elif, it's going to look very unpleasant to read. It's not going to be. It's very easy to introduce bugs in these things. So I would always recommend doing that using the match statement. Right. Now we're going to come to the next example, and this is the final example. It's also the most complex one. Is parsing an AST. How many of you know what an AST is? Okay, about half maybe. So it's AST stands for Abstract Syntax Tree. So what happens is that if you have a compiler, and the compiler wants to basically take the input program that you have, like the text that you see here on the left, and convert that into some kind of code. In Python, that would be code for the virtual machine. If you have a C compiler, it would be machine language. Then you convert everything that you see here, all the text, first into tokens. Tokens would be like, for example, the def or the if or the and, or like in a for statement, the for. Those would be tokens. And then you collect all these tokens and put them into a tree structure. And what I've shown here on the right, this is actually the output of the Python AST. And as you can see, it's a very deeply nested structure, very, very detailed. All the details that the compiler finds are put into these structures. And then the next step would be to then take that structure and convert it into bytecode. So what I wanted to do as an example here is I wanted to convert this way of writing things, which is the classic if-elif-else kind of approach to parsing, convert that automatically into code that uses the match statement. So, are you still following me? Yeah? Good. So I'm going to have a few slides showing all the different functions I used for that. The first one is this one here, the function that basically gets the function as an object and then uses the inspect module to get the source code for the object. Then you convert the source code to an AST using the AST module. You get a tree, and then you step through the tree, and because you want to not process everything, but you just want to process functions in there, functions that look like this, right? So I have to be a bit more specific to basically keep the example a bit shorter so that it actually fits on a few slides. What I do here is I take functions, and then the functions, they should have a variable, and the variable is basically the variable I want to match on, right? So if I have a function, and this is what I'm doing here, if I have a function that uses a particular name and then has a single variable here as a matching variable, I want to extract that information and then do refactoring on that. So in the code here, what I'm doing is I'm basically searching for functions that have a name, and I'm capturing the variable name of that single variable in here. If I put in a function with more than one variable, this wouldn't match anymore. And then what I do is I basically branch out to a new function refactor, which is there on the right, to actually do the refactoring of that particular function. Now, what happens in here is, again, I go through that function code, and I try to find all the if-elif kind of statements in there. So the way that that works is that I go into the function body, and then I try to find if statements. And the way if statements work in ASTs is that they have three components. You have a test that you try to check, and then if the condition matches, then you go into the body part. If it doesn't match, you go into the or else part. So if you write let me go back here. Oops, sorry. If you go back here, the if-elif kind of thing is looks very linear, but in the AST it's actually a deeply nested tree. So it goes down very deep into the structure. So what you do here is when you find something like this, then you start scanning that if, and you check whether you can actually match this. And then if you find something that you can refactor, I put these into the cases here, then you call another function to actually do the refactoring. And once you've done the refactoring, everything is very easy. You just take the node that you get from the refactorer, and you replace it with the if statement that you found. You replace the if statement with the new match node that you created for that. So what do you do if you want to scan the if and check whether it actually matches? Again, you go into the AST. There are two cases that I want to consider here. One is without a condition, and a second one is down here with a condition. Right? So over here, I'm matching the call is instance and then variable name type name, and down here, I'm basically doing the same thing plus an extra condition that I have down here. So what I have to do for this is, again, I have to look how the AST looks like for these kinds of calls. And I'm doing the first part in here, which is quite simple, and the second part has an extra Boolean expression down here, and you can see that in here in this case statement. Again, it looks a bit complex, but if you look at the details, you're not really doing a lot. You're basically just trying to find the is instance in here. Then you're using the variable name that you had in your function definition. You check that, and then you capture the type name that you want to check in this type name variable that you have there. Now, if something matches in these two cases that you have here, then you take the cases and you collect them in a list called cases. If you have an unsupported if variable, if variant, then you just basically return everything as it is. You don't refactor. And now, once you have everything in here, you also have to check whether the list actually goes down further and whether you have additional, elifs in your list of branches that you have in your if statement. And you do the same thing over here. You match the if, you check everything, you use the scan if recursively on these things, and again, you collect everything in cases. And now that we know what we can refactor, we do the actual refactoring. And that's very easy, because we just use the different cases that we have, and we create a new match node for these things, and put the data that we've collected into those match nodes. So once you've done that, you can actually run this code on the left side, and you automatically get the right side. Right. So those were the examples. Now some benchmarks. Of course, I'm always into performance, so I wanted to see how it performs. I compared the match variant with the corresponding if variable using is instance. And what you see here is basically a collection of benchmarks. All of these values are nanoseconds, so it's not really, it doesn't take a lot of time, but you can see that the match variant often is quite a bit slower than the if variant, right? So in most cases, it takes twice as much time. Except for one case, which is the list of integers, where it's actually a lot faster. And so it's interesting to be able to do these things and actually get faster code. There's also a very weird thing that I noticed, which is in here when you use capturing variables. I mentioned the two different ways of writing them, using as and the inline ones. And I created test cases for both. And I found that using the inline version is a whole lot slower than the generic one, even though they basically do the same thing. It's just a different way of writing stuff, right? And just as a reminder of how you write these things, I think this is actually a bug in the implementation. Not a bug in the sense that it does the wrong thing, but a bug in the sense that the performance isn't right. So conclusion for benchmarking is match is about 2 times slower than the if statement. And it's really nice for doing simple things like matching a list of integers, for example, or list of values in general. That said, this is not necessarily negative, because what we're still using in Python, even 3.13, is the first implementation of this. So after the PR got merged into 3.10, nothing much happened anymore. So there's still a lot of possibility there to improve things, to optimize things and make things faster. So it's definitely not a reason to not use these things. And the overall conclusion here is that match makes it a lot easier to write parsers, and it's also incredibly useful if you want to write readable code, right? If you compare this nonsense here with this kind of piece of code, it just looks a lot nicer. It's a lot easier to understand. And it's also not as error-prone as the left part. So I would always recommend doing these things, and always recommend learning new stuff as it comes along. Right, these are the resources. I already posted that before the talk. For the benchmarking, I wrote a new package called the micro benchmark package there. This makes it a lot easier to write micro benchmarks and run them. If you're interested in these things, then go have a look. It's still in alpha. It's still very much in development. But it's quite useful, and it makes writing micro benchmarks a lot easier. And you can, of course, then download everything, the tests that I did from the GitHub, and also run them on your machines. Maybe you get different results. Right, thank you.
Thank you very much for this very interesting presentation. So we have time for maybe 1 or 2 questions. Rodrigo asks, what you called an instance pattern doesn't really build the instance to do the matching, right? It looks like an instance, but it isn't one.
Yes, exactly. It basically it checks the type, and it checks the attributes that you put into that pattern. That's it. It doesn't actually build the instance.
And the other question is, do you know why was it decided to not support case fall through, like in switch case without a break? This seems to limit flexibility and promote code duplication.
You mean like what you have in C, when you forget the break, that it basically goes to the next one? This is a constant source of bugs, right? And it's because of course the CPython interpreter uses the switch statement internally, And we've had these issues, right? So we decided, well, it's not a good idea. So let's not do it.
Okay, that's it. Thank you very much.
Thank you.